Okay, so we're going to start the next lesson, ideal gas law. So as a quick review, we did these two, the second lesson, and then these two, the third lesson. And remember, this was just a combined equation for all three of these. And then the first lesson was just an overview of gases and the relationships between pressure, temperature, and volume that they all have. The only thing we're going to learn extra today is the ideal gas law, and that takes into consideration the amount of gas. If you notice all of these equations that we've gone over so far, it assumes the same amount of gas on each side of the equation, whereas the ideal gas law actually takes into consideration the amount of gas as well. So after this lesson, I want you to be able to explain what an ideal gas is, and I want you to be able to calculate an unknown pressure, temperature, volume, or amount of gas using the ideal gas law equation. So basically, an ideal gas, they assume that they're going to follow kinetic molecular theory, and they are going to conform to all gas laws. So some of the gases that we know of do not follow some of these laws, and so they don't obviously conform to these equations, is what basically that slide is saying. So these are all just the normal gases, none of the outliers or gases who do opposite of what we expect type situations. So up until now, like I have said, we've only changed pressure, volume, and temperature. So now we're going to change the amount. So the new variable is the N, and that's just the moles of gas. It's the amount of gas, and that way we can take into consideration how much gas we've used. So we do need to convert whatever amount we have, if it's not already, in moles. So here's the equation. I have written it here already, but you do have to use these exact units. You have to have your pressure in atmospheres, you have to have volume in liters, you have to have moles, and you have to have, this is just a constant, so don't worry, that's not going to change. And this is normal for you, you will have to have your temperature in Kelvin still, but this is new where you have to have them in atmospheres and liters. And again, that's just the constant. It is known as the Picky law because you can't use whichever pressure unit you like or volume. It has to be atmospheres and it has to be liters. Okay, so let's go over our first question. So at what pressure would 0.212 moles of a gas occupy at 6.84 liters at 89 degrees Celsius? So I just write down my variables, P, V, N, R, and T. Okay, so at what pressure, so our variable we need to isolate will be R, what am I doing? You don't isolate R, it's a constant. The variable we need to isolate is P. R is a constant, we always know it, we will never isolate it. Anyways, so what pressure would 0.212 mole, why do I keep putting things in the wrong spot? Sorry, I'm not thinking clearly, I guess. Moles are here, 0.212 moles, of a gas occupy at, this is the volume, so 6.84 liters at 89 degrees Celsius. So let's convert 89 degrees Celsius plus 273, 362 Kelvin. Okay, and then remember the constant is the same number every time, and that is 0.0821. The units is liters, atmospheres, over moles, Kelvin. Okay, so don't fret about the units. It doesn't matter in 10th grade. We just, as long as you keep everything the way I ask you to, we're good. So we need to convert, or we need to isolate P. So let's go ahead and just write our equation out. So P, we don't know, right? Volume, 6.84 liters. Okay, equals, the question gave us moles, so we don't have to convert. So 0.212 times the constant, 0.0821 times temperature. Okay, and before, you could, I like to multiply all three of these together and then start manipulating the equation, but this one's quite easy. All you're going to do is, to get P by itself, is divide 6.84, and you will have your answer. So let's shorten this up a bit so I don't have to write so much. So 0.212 times 0.0821 times 362. And that will be, we have three significant figures in all of them, so that makes it easy. So 6.30 over 6.84. So 6.30 divided by 6.84. And that equals, we have three significant figures on each, so 0.921. And the units have to be atmospheres. We don't have a choice. So there's our units. Okay. The next and last example of the ideal gas law is we're going to have to do some converting. So obviously, this is the easiest it'll be on the test. This one is going to require some work, which is good. We're going to do it together, no big deal. So the question, again, is at what temperature would 52.3 grams of methane gas occupy 65.7 liters at 184 kilopascals? So we're going to actually have to convert a couple of things. We're going to, well, let's write down our variables first. So P, V, N, R, T. So our pressure in the question, it says that it is 184 kilopascals. Okay, volume, it's 65.7 liters. Moles, it doesn't give us moles, but we can convert. It gives us grams. We can convert grams to moles, right? 3 grams, okay. Let's go ahead and put methane. Okay, and then R is the same, it doesn't change, 0.0821. Liters, atmospheres, over moles, Kelvin. Temperature, we don't know. That's what we're going to have to isolate. Okay, so we need to convert a couple of things. First, we need to convert this, right? Because we have to have it in atmospheres. So to convert, we'll put 1 atmosphere here. If you haven't gotten it in class, I have a paper of conversions for pressure and I think it's just pressure that I have conversions for that you can use. Maybe, I'm not sure. No, I'm not going to give you these. I might give you the constant. But yeah, for sure I'll give you these so you can convert. All right, so anyways, if you don't have it, grab one in class. It's just a couple of pressure conversion sheets or charts or whatever. 101.3 kilopascals is the conversion for atmosphere. Okay, so the kilopascals will cancel. And we're going to do 184 divided by 101.3. And the answer will be in significant figures. This is conversion, so 3 significant figures. So 1.82 atmospheres. Okay, this is in liters, so it's good. This is not good, right? We need moles, but we know how to convert to moles, right? This is what our last unit was. If you're doing this unit in quarter 2. But if you're waiting until quarter 3, there's no telling how long ago we did moles. But either way, you should know moles because I'm in the middle of teaching it now. So grams of CH4 will go here, and we need to convert to moles. So for every 1 mole of CH4, let's see how much it'll weigh. Carbon is like 12.011 plus 4 hydrogens, and it weighs times 0.00. We're just going to do that. Okay, so the molar, and I got these numbers off the periodic table. Those two are very common, and so you'll probably have it memorized too, but if not, you could have found this number and this number off the periodic table. So the molar mass of methane is 16.343. Okay, so significant figure 16.043. Okay, and the grams will cancel and we'll be left with moles like we need. So 52.3 divided by 16.043. We need 3 significant figures, so 3.26 moles CH4. Okay, so we have our pressure. This was already good. We need converted, we're okay. This is a constant, we're good, and this will be what we're isolating. So we finally have our variables. So this is obviously what the test will look like. Not necessarily the easier one we did prior, but we all have to start somewhere. So our equation, we're just going to plug in some numbers. So pressure is 1.82 atmospheres times the volume, which is 65.7 liters, equals moles, which is 3.26 times the constant, 0.0821, and we have temperature, okay? So we're just going to divide everything by 3.26 times 0.0821, okay? So now we just calculate it. So T will equal, okay? T will equal 1.82 times 65.7. So 119. We have 3 significant figures, so this actually needs to be 120. Okay. Okay, and then we need to take this, 3.26 times 0.0821. And we have 3 significant figures as well, so 0.268. Then we divide. And the temperature is 400 We have actually, that's two significant. I should have put a dot there. 3 significant figures, so 448 Kelvin is our answer.